Okay. Good day, class. This is Dynamics of Rigid Bodies, Lecture 1, Rectilinear Kinematics. My name is Engineer Ralph Norman Malana. I will be your instructor for this particular course, this second term. The course code is ME266. Everything about this class, the course plan, the schedule, can be found in your Canvas. What to expect? For this particular lecture, you'll be discussing about rectilinear kinematics, continuous and erratic motion, talking about what displacement versus position, what is velocity and acceleration in average velocity, instantaneous velocity, and or average acceleration and instantaneous acceleration. There is also the concept of constant velocity and constant acceleration. For you to be successful in understanding this, you have to have a basic understanding of differential and integral calculus, what rectangular coordinate systems are, your basic trigonometry and geometry, and of course solving kinematic problem via graph analysis. Um, we don't need a graphing paper for this, but you could draw it on your paper. Right? And of course, we'll have to deal with some sample problems later. Okay, so we are with dynamics now. It's one of the main sciences under mechanics, where it involves how objects and systems respond to applied forces, leading to an understanding of their motion, acceleration, and the forces acting upon them with respect to time. It's the only thing missing there. The kinematics, on the other hand, is the branch of mechanics concerned with the motion of objects without reference to the forces which cause the motion. Okay. Here with rectilinear kinematics, we refer them to straight line motion. We have horizontal, vertical, and then we have also projectile motion, which is a combination of both horizontal and vertical motion. We have several variables here. We'll start off with position, then displacement. With position, it refers to the location of the object along the straight line at any given time. The units are meters, feet, and there we go. And position usually can be position coordinate here could be positive or negative here. Distance, on the other hand, is just scalar. Okay. Now, with displacement, on the other hand, it refers to the change in position of an object at some time interval t. Normally, it's represented by delta s, or change in position, basically. And this is with respect to time. Time gives legitimacy that an event has occurred. So normally, this is the formula you familiar with. The displacement, or basically change in position, is just simply the difference between final and initial position. The suffix x and or y here just pertains to what axis the object is traveling in, whether it's traveling horizontally or vertically, or sometimes even both. The next term that we're going to be talking about is velocity. And let me just load up the screen here. There we go. Velocity and instantaneous velocity. There we go. So we'll just focus our attention here first. Velocity, or more commonly, the formula that we usually know is the average velocity. V sub A average, basically. It's represented by meters per second in metric, or feet per second in English. It's simply what the velocity is simply the ratio between the change in change in position with respect to time, or basically the ratio of displacement over a time interval, delta t. It could be positive or negative depending on the location it's pointing. In a position time curve or displacement time curve, um, if you get a linear graph going up, the slope of the line here is basically that's your velocity. Okay? Because that's how the formula works. Delta S, so that will be final position minus initial position divided by final time minus initial time. More commonly, hindi na natin sinasama yung delta T because in most physics books, the initial time is basically 0 seconds. So just for, nomenclature's sake, we're just gonna keep it lang naman. Of course, there's what we call average speed. It's a scalar version of velocity. Velocity is a vector. Here, we're just gonna be talking about distances. Velocity is just simply, just the distance traveled divided by um, the time interval t. Now, unfortunately, with average velocity, instantaneous velocity is kind of different. With average velocity, especially when you're given a time frame from A to F, something like this one, we're talking about the total velocity and we just add them up together, rendering with an average amount of velocity here. But with instantaneous velocity, we are referring to the instantaneous velocity, to the velocity at a particular moment in time, okay, with respect to time at a single point here. So the average velocity is represented here by the secant line along the curve, but we're referring to the instantaneous velocity as the tangent of the line here, where the formula is pretty much the same. It is still the first derivative of position relative to time as time approaches to zero. Or another way to read it is simply ds over dt as delta t approaches zero. Now, we have also called constant velocity. The thing with constant velocity is that when you have a constant velocity, instantaneous velocity is the same as the average velocity, which means they would have the same formula. So we have the V average of delta S over delta T. We know the instantaneous velocity is simply the first derivative of position relative to time with respect to time, or ds over dt, the change in position with respect to time. With constant velocity, they're pretty much the same. Okay, so here's a position time graph, and here's a line, equation of the line. The slope you get here is basically your velocity. Okay, now at constant velocity, like the definition would have told you, it's the same. So the constant velocity is the same, whereby instantaneous velocity is equal to average velocity, which means we can substitute the formulas of delta S over delta T with the difference between final position and initial position, SF minus ST divided by delta T. Now, with this particular formula, we can actually rearrange it so that we can find the final position if we're given initial velocity, we're given constant velocity, and we're given the time interval. And rearranging the equation with this particular equation, it's one of your basic kinematic formulas. Okay. We're going to be talking about acceleration in a few, pero if you choose naman yung velocity time curve, if the slope of the line for the position time graph is a velocity, the slope of the line of a velocity time curve is simply called acceleration. But more on that later. Okay? So this formula would work assuming that your velocity here is constant. Okay? It's not gonna be apparent a problem, but you have to take notes of how the problem would describe your velocity is. Is it instantaneous? Is it average? It's okay if it's average. You still can compute for average velocity if you have both positions naman there, a final and an initial one. Let's do some sample problem for this. Here, find the displacement and average velocity of a moving car between positions A and F. So in this particular case, we have this particular graph here with an initial position of 30 meters and a final position of 53 meters, or in this particular case, negative 53 meters, since it's got past its point origin. Okay. So visually, it looks kind of something like this. A went to B, then C, then D, then pass here. So from right and goes to left. So in our nomenclature, positive goes right, negative goes left. So what do we do? So we're here to find displacement and average. And displacement just simply means change in position. So we have the final and initial position. So that's going to be negative 53 meters minus 30 meters. That would be a total of negative 83 meters. Now to find the average velocity here, it's going to be delta S over delta T. And it's just simply negative 83 meters divided by the total time, which is 50 seconds. So 50 minus 0 seconds, which gives us negative 1.66 meters per second, or simply put 1.66 meters per second to the left. That's how it is. How about here? We are to find the velocity of a runner running along a straight line at a constant rate was recorded by starting the stopwatch at the moment the runner passes a given point and stopping it once past another point 20 meters away. So the time travel is indicated on the stopwatch. The total time traveled here is 4 seconds. Find the following. What is the runner's velocity? And B, should the runner continues after the 20-meter point, what is his final position after 10 seconds has passed? So with here, A, we need to find the velocity along the horizontal axis. So to get that, we know that delta S or delta X in this particular case divided by delta T. So we have your final position minus initial position. Initial position is assumed to be on a starting point, so that's gonna be 0. And we have here the total time elapsed as 4 seconds. And we have here the final position at 20 meters. So the runner's velocity here is 5 meters per section. So 5 meters per second. This velocity is not just average velocity, but it's also considered a constant velocity because the problem described the velocity of a runner is to be at a constant rate. So that should be your clue that this velocity that we just solved is the constant is a constant velocity. Now, should the runner continues to run after the 20-meter point, what is his final position after 10 seconds have passed? Now, the formula here, the problem that's being described here is what if he didn't stop at the 20 meters, so he keeps on continuing. So meaning it's implicitly implying that the runner started from point zero and the total time passed instead of 4 seconds now, it's 10 seconds. Okay. But our final position now is not 20 meters. So what it is, what is it? So we're finding SF. And we have constant velocity rate, but we also have initial position. So in short, we can use the previous formula that we derived earlier using this one. XF is equals to initial final position is equals to initial position plus the product of the constant velocity times time interval. In this particular, the total time interval here is 10 seconds. The initial position here is not mentioned, so we assume it to be 0. And we have the constant velocity of 5 meters per second here. So the final answer, the final position here would be 50 meters. The next important variable for rectilinear kinematics is acceleration. In this particular case, the average acceleration, which is basically the ratio of the change in velocity with respect to time, or final velocity minus initial velocity divided by delta t, or tf minus ti. Okay, the units are there, so please be mindful of them. Okay, so again, just like I mentioned earlier, on the velocity time curve, in a displacement in a position time curve, the slope of the line there will be velocity. In a velocity time curve, naman, in a velocity time curve, naman, the slope of the line would be acceleration. So just like velocity, acceleration is a vector, so it could be positive and negative. If we have instantaneous velocity, we also have instantaneous acceleration, wherein this is the acceleration of an object at a particular specific moment in time. Where we describe it, it's still the ratio of the change in velocity with respect to time. But if we're just going to derive it, it's going to be the first derivative of velocity with respect to time as t approaches to 0. There's also a relation between acceleration and position in terms of calculus in the derivation. It is all you can also find the instant acceleration by the second derivative of displacement with respect to time squared. Okay? So basically, yeah, this is gonna be useful, especially when when there's no specific formula that you can use. Okay, so the only thing you can remember here that will be dvx over dt. Okay, So with velocity, instantaneous velocity is just simply ds over dt. With instantaneous acceleration is dv over dt as t approaches the zero. Okay? So derivative of vt, second derivative of position and time. There we go. The next one is, of course, kung meron tayong constant velocity, we also have constant acceleration. Now, there's no animation here, so we're going to go walk through this one by one. So here we have your definitions. Okay, with constant acceleration, it's a condition whereby the instantaneous acceleration is at any given time is the same as the average acceleration. So as you recall, instantaneous acceleration is just simply the change in velocity with respect to time t as time approaches the zero. So it's dv over dt. We also have, if you're familiar with the instantaneous velocity is the derivative of position with respect to time as time approaches to zero. So here, ang formula ng constant acceleration is equal to that of the average acceleration, which is simply the final velocity minus initial velocity divided by delta time t. Now, rearranging the equation, we could also get the average velocity here as the initial plus final velocity divided by 2. We can further extract this equation using just a graph here, as you can see. Especially if it's just pag constant yan, it's just gotta be a straight line. It's perfect. Constant acceleration is perfectly a 45-degree angle lang yan. Okay, and then makukuha mo yung average dyan. Okay? Which is something that you can use using constant velocity problems. Okay? So here, a constant acceleration and velocity per unit time varies linearly. Okay, so base times height. There we go. Now, to derive the other kinematic equations, we take these three functions: velocity as a function of time, position as a function of time, where time is equals to zero, at t equal to zero, and then of course, what if we were not given time, but we're given only, we're only given position, and one of which is unknown, whether acceleration and velocity. So here, velocity as a function of position naman. Okay, so we're gonna be starting first with velocity as a function of time here. As you can see, referring to this formula, dv, a or constant acceleration. These are all applicable when your acceleration is constant. So at constant acceleration, AC is equals to dv over dt. So that's still the same formula, the same way with these guys, provided they're given. And you just have to integrate them. So we know that there's a final and initial velocity. And of course, the final and initial time, that's usually zero. And this one is a particular time t. In this particular case, AC is constant, so lalabas lang siya. Ang integration naman ng dv naman ito, that's gonna be vf minus vi. And rearranging the equation, we have the familiar formula of vf is equals to vi plus ac delta t. Now, using the same formula, the position as a function of time at time equals to zero, so v is equals to ds over dt, whereby ds, rearranging the equation, so ds is equals to v dt, where v here could be equal to vi plus ac delta t. Okay? And integrating both sides of the equation, so we have new final and initial positions, final time and initial times, or t time, t final at particular t, and then initially is usually zero naman. Hence, nakalagay zero dito. Integrating both, we will have the equation sf minus si, and here magiging the initial velocity times t plus ito magiging act squared over 2 as you would dictate pagdating sa integral calculus equations natin. Then finally, here we have velocity as a function of position. So we have here a dv dt and v equals to ds over dt. So they are both as a function of position. We don't need time here. So rearranging the equation here, equating both cells as dt, magkakaroon tayo ng v dv equals to a ds, integrating both sides of the equation with its limits, final velocity and initial velocity at its upper and lower limit respectively. And then here we have final position and initial position as its upper and lower limit, ACDS. So constant acceleration dito, lalabas lang to. So yung integration lang naman ng SF SI ds, that will be SF minus SI. Here naman, so here magiging, hindi siya constant, so that's gonna be V squared divided by 2. So that's gonna be VF squared divided by 2 minus initial velocity squared divided by 2. So rearranging the equation, we will have this particular equation. Vf squared minus Vf squared is equals to Vi squared plus 2 times AC delta S, or SF minus SI. Okay, remember, these are only applicable when your acceleration is at constant. Okay, so if calculus may prove difficult on your end, you could also extract the formula using a simple graphical method here. For example, we have a velocity time curve. We know the equation of the line here is delta v is ax, is acceleration, whereby the formula for the average acceleration is just delta v over delta t. Now check out the shapes here. We have a triangle and a rectangle, and you can definitely the kumbaga sa position time graph, yung slope of the line doon is simply yung ano, yung velocity. Sa velocity time graph, yung slope of line is acceleration. Yung area under the curve ng velocity time graph, you're able to get what are you able to get dito? It's just simply displacement. Kasi velocity here time graph, yung area under the curve here, that will be yung total displacement mo dito. Okay? I'll show you why. So all you have to do is just get the area of these two shapes. We know the area of the rectangle is just simply base times height. So our base here is time, our height here is initial velocity. So there you go, VOT. And then of course for triangle, that's gonna be base times height divided by 2. So our base here is time. Our height is the difference between this final point and this particular point. So it's gonna be final velocity minus initial velocity times time divided by 2. There we go. And to get the area under the curve of velocity time graph is your total displacement, okay, or change in position. So all you have to do is just add them together, so these equations. So finalizing formula, you would get this one. And another way to represent delta S is simply delta S is the Vf plus Vo, final velocity plus initial velocity divided by 2. This is your average velocity times time. So it's the same way we did here. Where is it? Here. This is your V average done. So that's it's the same way we did it here. Our first kinematic equation, delta constant velocity here. Yeah, here. Vc times delta t. Or if it's a constant velocity, it's also equal to your average. Instantaneous equals to V average, right? So we go here. There we go. Whether your acceleration is constant or your velocity is constant, that should be applicable naman dun. Now we have another form of acceleration under the free falling object condition. So yung basic assumption natin dito, air resistance is neglected and yung variations ng gravity will, with respect to changes in altitude, is neglected dito. Now, an object is considered in free fall when it is only subject to its influence in gravity. So if remember, we have these particular equations. Ang mangyayari dyan, we're just gonna change it to G, where G here is negative 9.8066 is going downward naman. Okay? So here's the summary of equations. Here's a constant velocity, constant acceleration, and then of course, free falling body dito. That negative G there is gonna be substituted inside, okay? So hinayaan ko lang siyang positive dito para hindi kayo malito. Then of course, when given equations for constant acceleration, use calculus, whereby here are your sets of given formulas naman. You don't have to remember all of them at the same time. You just have to know at least 3 or 4 formulas where you can derive all of them naman eh. Let's try. Here's sample problem number 4. We're given a particle with an initial velocity of 12 feet per second and at an initial location of 0. Determine the final position when the time is at 10-second mark and if the acceleration is also at 2 feet per second squared to the left. Okay. Okay. So you can, if you're not familiar yet with the equations, you can simply write down muna yung given na meron kayo. So you know you're given with a 0 position. You know you're given with a 12 feet per second velocity, initial velocity. And you know very well that you're also given with a negative 2 feet per second squared. This is going to the left. And a total time elapsed of 10 seconds. You're asked to find the final position. One of the formulas we can use is simply SF is equals to SI plus initial velocity times t plus AT squared over 2. We just simply substitute the equation here. Do your unit analysis so that you know what units to be canceled. And then you will have an answer of 20 feet. Another one is here. If S is equals to 2t cubed meters, where t is in seconds, determine the velocity when t is equals to 2 seconds here. So sample problem 5 and 6 is different because you're represented with a variable that is represented by an equation of a line. So one of the few things you want to do is just write down the given muna. So we have an equation here. Cube here seems like a hyperbola or parabola. If I'm gonna draw yung curve net, it's gonna look something like this one. So position time graph should look something like this one. Then of course, if you recall, the velocity is simply the derivative of position with respect to time, ds over dt. And all we have to do is just substitute our equation 2t cubed. So doing that, we have this one. And we have the limits of 0 seconds to 2 seconds. Okay? And then substituting time at 2 seconds, so that's going to be 2. That's going to be 4. 4 times 6. So your final answer is 24 meters per second. Now, with sample problem number 6 here, 4t plus 5 seems to be a linear graph naman. And we're asked to find what is the acceleration when time is equals to 2 seconds. So if we're going to graph it, it's going to look something like this one. There you go. And then recall the equation a dv over dt. So we just have to substitute the equation of the line 4t plus 5. So that's going to be d equals to 4t plus 5. Or here it's just the derivative of this 0. This one is going to be 1. So that's going to be just 4 meters per second squared. That's hell a lot easier. Let's try with sample problem 7 and 8. Here we have a is equals 4 meters per second squared. Determine the position when t is equals 3 seconds if the velocity at is equals to 2 meters per second and the initial position is 2 meters when t is equals 0. So indicating that v here and s here are initial values or initial parameters because we're indicated that when t is 0, these are the parameters. So we're here to determine the final position when t is equals 3 seconds. So write down your given as such. And then our solution here, so final position is unknown. We're given initial position, we're given initial velocity, we're given acceleration assumed to be constant. So we can use this particular formula. Okay, and it's positive. And we will get an answer of 26 meters. Here, we're represented with a variable where a here is equals to s meters per second squared, where s is in meters. Determine v when sf is equals to 5 meters, and if uh, determine the final velocity. Actually, wait lang. Determine velocity when the final position is 5 meters. If if velocity at 0 meters is 0 meters per second, and at if the final position, sorry, wait, let me read that again. So determine the velocity when the position is in 5 meters, whereas when the velocity is close to 0 meters per second, the initial position is 4 meters. So our solution here, so we don't have time dito. So we can definitely equate this is velocity with respect to position. So if you recall, v is equals to derivative of position with respect to time, and acceleration is the derivative of velocity with respect to time as time approaches to zero. Rearranging that equation, we have this particular one, AdV, the AdS equals to VdV, okay? And now after this, we integrate, okay? So A here is just simply S, SDS, and equals to VdV, and we proceed with their limits. So when it comes to the position, we have the upper and the lower limits being 5 meters and 4 meters. There we go. And then we have final and initial velocity as the upper and lower limits for VdV. And integrating them would result to SF squared minus SKI squared, and then VF squared minus VI squared. So 2 will be canceling out. And then the final here will be simply 5 squared minus 4 squared plus 0 squared. And, square root of them. So your final velocity here is 3 meters per second. It only looks complicated, but it's a lot easier to solve, honestly. Here, the car moves in a straight line. That for a short time, its velocity is defined by v is equals to 3t squared plus 2t feet per second, where t is in seconds. Determine its position and acceleration when t is equals 3 seconds. So when time is at 0 second, your position is 0. So meaning your initial position here is 0 as well. So recall, we have this one. So we're here to determine the position and acceleration at t is equals 3 seconds. So our solution here, it's gonna look like that, 3t squared plus 2t. If you could remember, our solution of v is ds over dt. So for position, we can simply substitute it. The limits here is t is equals to 0. We have t here at 3 seconds. V here is represented 3t squared plus 2t. And we have s initial position 0. And that's what we're looking for. That's final s. Okay. So expanding this equation, we will have this one. And substituting the values we want, that's gonna be t equals to 3 seconds. There we go. We will have, and then for A, it's gonna be AdV over dt. There we go. So we have 36 feet. And then for A is equals to the derivative of velocity with respect to time. We already have yung velocity, which is this one, 3t squared 2t. So all we have to do is just derive them. That's gonna be 6t plus 2. So at t equals 3 seconds, that's gonna be 6 times 3, then plus 2. So your acceleration here is 20 feet per second squared. All right, continuing. So we have here sample problem 10 is one of the free falling examples I have here. Here we have a figure of a rocket in a test launch site. So, and then here's a trajectory represented in blue line. Seems to me the rocket here starts at a 40 meter And then it has an initial velocity at VA at 75 meters per second. Goes up to point B. It traveled a position SB here. There's also an S here, position here. So at this particular point, this is it just below, it hits just below the ground. That's your point C, and then O. Okay, so during a test, a rocket travels upward at 75 meters per second, as I mentioned earlier. When it is at 40 meters from the ground, its engine, say 40 meters from the ground, its engine fails. So meaning there's no propellant here. Determine A, the maximum height reached by the rocket. So A, maximum height reached. B, its speed just before it hits the ground. Hit the ground. So that's going to be point C here. And while in motion, the rocket is subjected to a constant downward acceleration due to gravity. Neglect the effect of Earth's resistance here. So let's just write down our given. We know our given here as 75 meters per second and position here, initial position at 40 meters. We're here to find the height max or S max. We call it SB na lang. Then, of course, we're here to find rin yung final velocity just before it hits the ground. Okay, so what do we do? So for it to hit its maximum height, your velocity must have, your final velocity must be zero before it, goes back again and start gaining speed or velocity. So at max height, kung pinaka-common dun, your final velocity should be zero dun. So, and with that particular case, we also know that the rocket is subjected to constant downward acceleration of gravity, which we know is negative 9.8066 meters per second squared. And at this particular point, at max height, your final position is at its highest. So that's going to be your S max there. We also know our initial position. So we can use definitely this formula whereby velocity squared, final velocity squared is equals to initial velocity squared plus 2 times G and times delta S, which is SF minus SI. It's not a product, SI yan. Minus, it's a difference in SI. Yeah. Let me just edit that a bit. Paano ba? Pen. There we go. Anyway, it's not editing. So here, that's minus. There we go. Yeah. Okay, it's not showing. I don't know why. There. Huh? Okay. So the next here, we just have to rearrange it so that our unknown is on the left side and all the known values on the right side. Just like so. And then we just have to substitute all the known values. So we know that our final velocity at max height is 0. Our initial velocity here is 75. And divided by 2 times 9.8066 plus our initial position of 40 meters. There we go. All we have to do is just cancel all the equations here. So we have meter, this is going to be meter squared per second squared. This is meter per second squared. This is going to leave us with meters lang. So pares na tayo ng units. So the SF or the maximum height at point B, that's going to be 326.7966 meters or 326.80 meters. Okay. Now, the next question here is the final velocity just before it hits the ground. So it's going to be here, starting here, and then the final velocity just here. So in this particular sense, the final velocity from A to B is now our initial velocity from B to C. So we know that's going to be 0. And now our final position here is going to go back to 0 here. So let's do here. And our final position back then from A to B, that's error B max, is now our initial position. So that's 326.7966 meters. Okay? And it's gonna be swap lang naman. So it's still, we could still use the same formula. This one. We just have to rearrange the equation here. So yeah, by squaring both sides of the equation. So magiging VF is equals to the square root of VI squared plus 2G SF minus SI, except we have all the known values dito. So our VI here is still 0 meters per second. because that's our initial velocity na dito. Yung final natin is just magiging initial velocity at point B to C. So that's still 0. And then this is negative 9.8066 pa rin. And then of course, yung final position natin, which is at this particular point, is gonna be 0. This is yung final, just before it hits the ground. And yung initial position na natin is our S max, which is negative 326.79 minus 326.7966 meters. And we just solve it. So our final velocity at point C, that's gonna be 80.0594 meters per second, or simply 80.06 meters per second. Okay. So that's for your continuous motion. The next lesson is actually called continuous versus erratic motion. So over the past few problems, we observe and analyze the relationships of displacement, velocity, and acceleration with respect to time in a seamless continuous motion. However, reality is not all straight lines and keep parabola. Often we have a naturally change vector in real time. Here are samples. This is a velocity acceleration time graph of a space rocket. We have throttle down, throttle up, throttle down, separation. I forget SECO, multi-entry. I forgot the acronym here. Then of course we have here for F1. So we have a bunch of graphs for position, time graph, position, velocity time graph, and acceleration time graphs here, which they need to, analyze how to properly attack the racetrack dito. For us, we get this one. So we're gonna be dealing still with parabolas pa rin naman. And normally, it's gonna be represented sometimes as a constant. In this particular velocity time graph, it seems to here that from 0 to 10 seconds, the vehicle here is accelerating, and somehow from 10 seconds to 60 seconds, the vehicle here is now decelerating at a particular pace shown in this equation, in this particular line graph. Here it's very linear. You could say it's almost constant acceleration here. So continuous motion. And here we have 0 to 10 at 10 meters per second. And then from 10 to 60, we have negative 2t plus 120 meters per second. Very erratic motion. Here's a sample. Fortunately, we already had practice in terms of, graphing them up. Okay, and show the relationship between displacement, velocity, and acceleration here. And acceleration under erratic motion. So let's draw a sample here. Here's one of the examples. Given a position time graph of s is equals to negative 2t plus 2, draw the acceleration time graph and the velocity time graph. So in this particular case, at 0, it starts at 2 meters, and then at 1 second, it goes to 0 position. So recall that the velocity is the derivative of position with respect to time, and acceleration is the derivative of velocity with respect to time. For VT graph, all we have to do is just substitute it. So and get the derivation here. So V ds dt, substitute the derivative of negative 2t plus 2. That's gonna be negative 2 meters per second. And for your acceleration time graph, you substitute the velocity you got here. So that's gonna be d negative 2 dt. So your acceleration here is 0. So mathematically and by calculus, you've shown that for any linear it seems to be at a constant velocity dito. Hence why it's kind of decelerating. And your acceleration, there's practically no acceleration at all. Okay? So if we're gonna graph yung VT, so we draw yung VT curve. So ito yung we use yung same time interval 1 second. So from 0 to 1, it's just negative 2 meters per second squared. Negative 2 meters per second. And to check, the area under the curve should be, ng velocity time graph should be your total displacement, or your delta S. So all you have to do is just that 1 times negative 2, that will be negative 2 meter as your total displacement. So that's 1. Okay? So for your acceleration, since your acceleration is 0, from 0 to 1, so it's just gonna be a line lang dun from 0 to 1. That's it. Let's try naman something else. Here is a bicycle that moves along a straight line, and such that the position is described by the graph below. So from 0 to 10, it has a displacement of t squared. 10 seconds to 30 has a displacement of 20t minus 100. Okay, we're here to construct the velocity time graph and acceleration time graph for 0, uh, 0 to, in between 0 to 30 seconds, basically. So how do we do that first? Recall we have, our equations of the line. The velocity is the derivative of position with respect to time. Acceleration is the derivative of velocity with respect to time. We start first with 0 to 10. So we represent 0 less than equal to t, where t is less than equal to 10 seconds. So we're going to be working with that. And we start with our equation s is equals to t squared. So we substitute that and we will get 2t feet per second. It's fine. And now you substitute that 2t now here for your acceleration, and you will get 2 feet per second squared. So to throw, okay. And next up, we will use naman yung 10 seconds, less than equal to t, and then less than equal to 30 seconds. So yun yung boundary natin. So here, we will use the equation of 20t minus 100. So we will have 20 feet per second dito. And if you're gonna substitute UV here, dito sa a dv over dt, that's gonna be 0. So, 0 acceleration at all pagdating dito. So here, from 10 seconds to 30 seconds, constant velocity lang siya. Okay? So to draw yung graph, we start first again with 0 to 10. It's gonna come up linearly. That's v2t. So that's how you know it's gonna be linear. And then from 10 seconds to 30, it's just straight up 20 feet per second lang. That's constant velocity lang. Okay? Okay? Ang pinagkaiba naman with your acceleration time graph, mangyayari dito, from point 0 to 10 seconds, it's accelerating at a constant acceleration of 2 feet per second squared. Which is, kung constant acceleration yun, yung velocity time graph mo is very linearly going up. Okay? In its positive direction. Then, from 10 seconds to 30 seconds, your acceleration just simply drops because you now maintain a velocity, constant velocity of 20 feet per second. Hence, no velocity, no acceleration at all. So, yun yung pinaka-representation nun. So, graphically, you now understand what it looks like and ano nangyayari in real life. There's a lot more examples in the book. You could start by answering your problem sets. The deadlines are set na sa Canvas. So be sure to, ask questions there if you have any, and especially with the instructions on how to submit it. These are the problem sets, and that's the end of lecture 1.